Welcome to this next video in the playlist on topology. In this video what we're going to talk about is the concept of a topological subspace. Okay, so to start this off then, we're going to start with a recap of what a topological space is, so that we've all got that fresh in our minds, and then we'll have a look at how you can create a topological subspace of a topological space. Okay, so firstly then, the topological space. So topological space starts off its life as just a set. So I'll draw that here. So this box here, this will denote my set, capital X. Okay, and I'll colour it in green. And this is just going to be a set of symbols. And then what we're going to define on this is a topology. And defining a topology on this set will elevate its stature from just being a set of symbols to being a topological space. Okay, so what is a topology? Well, a topology, as we've seen in previous videos in this playlist, is a subset of the power set of X. Okay, so we'll denote the topology tau as usual, and it is going to be a set which contains subsets of the set capital X, i.e. it's going to be a subset of the power set of X. So the power set of X, remember, is the set that contains every possible subset of the set capital X. So you can take loads of different subsets of the set capital X. Even if it's just finite, you can take a huge number of different subsets. If it's infinite, it becomes unbearable to actually think about how many different subsets there will actually be. But you take absolutely every single one of them and you stick them into a set, and they'll be the elements of the set, and that's called the power set of the set capital X. And our topology tau is going to be a sub-collection of those subsets of the set capital X that are all in the power set of X. Now, this topology tau, it needs to obey some nice properties in order to actually qualify as being a topology. So you're not allowed just to take an arbitrary selection of subsets from the power set of X and expect it to be a topology. It has to be very well picked. You have to pick the subsets from the power set of X that you're going to include in your topology very, very carefully if it's going to be a topology. And it needs to obey 3 axioms that I will just list out here. So we'll start off with property number 1 here. So property number 1 is the easiest to understand, the easiest to actually achieve. This just says that there are 2 subsets that must always be in your topology tau, and these are the empty set and the entire set, capital X. So you're going to insist that the empty set, which is the subset that contains absolutely no elements at all, and the entire set, which is the set that contains absolutely all of the elements of your original set, capital X, you're going to insist that those 2 subsets are always in the topology tau. Okay, so they are 2 subsets of the set capital X, and you're going to insist that these 2 subsets are always in your topology tau. So that's the easiest to actually understand, because if you were to create a topology tau for this set capital X, you just start instantly by putting in those subsets. You put in the empty set and the entire set as your first 2 topologies, and you could stop there. This actually obeys all of the properties of a topology. If you just stop there, it does end up obeying the other 2 properties that I haven't listed yet, and it's called the chaotic topology. But often we want to go further because the chaotic topology usually isn't that useful. Okay, so what other properties then are we going to insist that our topology must obey? So property number 2 then says that if you take any 2 subsets of the set capital X that are in your topology, okay, so I'll write this out for all U1 and U2, so we usually denote subsets of the set capital X that are in the topology with a capital U, like so. Okay, it's the old notation for an open set, because the sets that are in the topology are called the open sets of the set capital X if it's going to be elevated to a topological space through this topology. Okay, so for all open sets, U1 and U2, that you can possibly pick from your topology tau, okay, so pick any 2 sets from this topology here, and if you intersect them, so you can intersect them, U1 intersect U2, so just drawing this on this picture here, we'll have one set U1 here, which is a subset of X, we'll have another set U2 here, which is another subset of X, and now what we're doing is asking look at the intersection of these two here, U1 intersect U2, the answer to that is a subset of capital X, and that must also be an element of our topology capital tau. Okay, or little tau rather. So you're always going to insist that no matter which two elements that you can pick from the topology, if you intersect those two together, that answer must also be in the topology. So this topology, it's starting to be quite a difficult thing to actually construct, okay, because you're going to have to design it very well. So you're going to have to make sure that if you take any two elements in your topology, any two of these chosen subsets that you've picked, that when you intersect them, you do actually end up with another subset that's in that topology that you've picked out. So it does need to be well defined. And axiom number 3 then, so the final axiom is axiom number 3, and this concerns what happens if you union together two subsets that are in the topology. Okay, so we've had property number 2, which is intersection. Now we're going to have a union, and this says that you can union together an arbitrary number of open sets from your topology, and the answer must still be a subset that is in your topology. Okay, so for all U alpha, okay, so now I'm indexing my open sets here with the subscript alpha, with this index alpha, and this doesn't necessarily have to be a finite index. It doesn't even need to be a countably infinite index. It can be an uncountably infinite index. All I need to know is that all of these sets here are in the topology. If you perform a great big union here, so you union over all of alpha, and you union together all of these open sets U alpha, the answer to that must be back within the topology tau. Okay, so when you union together an arbitrary number of open sets from the topology tau, you must get another subset of the set capital X which is in the topology tau. Okay, so those are the 3 axioms then that a topological space must obey. Okay, so there we now have fresh in our head the concept of a topology, and together the set capital X with a topology defined on it is called a topological space. And of course, for any set capital X, there is more than one topological space that you can create from that set, because there is more than one topology that you can create for that set. Okay, so the topological space is not just the set, it's the set with your chosen topology that you've constructed for that set capital X. Okay, right, so now to move on to the concept of a topological subspace. Okay, so how do you construct a topological subspace? Well, the idea is very simple. So I'll draw out my set capital X here again. So here's my set capital X, and we're now assuming it's a topological space, so it's got some topology defined on it here, tau. Okay, so what you're going to do then is you're going to find some subset of this set capital X, and we're going to actually create it into a subspace, a topological subspace of the topological space capital X with its topology tau. Okay, and this subset that you choose, it doesn't necessarily have to be an open subset. It doesn't necessarily have to be in the topology itself. So I'm just going to take a general subset of my set capital X. So I'll call this general subset capital S, and it's just some subset of the set capital X. Okay, so I'll highlight this up in orange. So this is the subset S, which is a subset of capital X. Okay, so just some general subset of the set capital X. And what I'm now going to do is I'm going to take this subset capital S and I'm going to turn it into a topological space in its own right. And this topological space that's contained within our initial topological space, this will be called a topological subspace. Okay, so what you can imagine doing is pulling this subset capital S out of the larger set here. Okay, it after all exists in its own right. It doesn't just exist as a subset of the set capital X. You can pull it out of the set capital X and have it existing in its own right. It's still just a set containing lots of elements here. Okay, so here is my set capital S now pulled out of my larger set capital X and existing on its own in its own right. And what I now want to do is equip this set capital S with a topology and turn it into a topological space in its own right. And then we'll call it a subspace of our original topological space, capital X. Now, there is a very, very natural way to put a topology on this set capital S. I mean, of course, you could come up with some totally random one. Okay, you could come up with your own one. This is, after all, a set in its own right. Okay, so you could just come up with some brand new topology. But there's a way of putting a topology on here using the topology that's on X. That is a very, very natural way of putting a topology on this subset. And that topology that I'm going to put on is what's known as the inherited topology or the induced topology from the larger subset. So, from the larger set. So the subset S is going to inherit a topology from the larger set capital X, is what we would say. Okay, right. So what I'm going to do is I'm going to create a topological space which is going to be our set capital S here, and it's going to have a topology on it, and we'll call this topology the topology tau from the larger set capital X, and then we put a line here, and then we put S down here. And the way that you would read this is the topology tau from the larger set capital X restricted, so that line here means restricted, down to the subset capital S. So that's the way that you would read this. Okay, the topology from the larger set capital X restricted down to the subset capital S. Okay, so what actually is the definition then of this topology? Okay, so it's going to be a set of subsets now of our set capital S. Okay, that's just the definition of a topology, and it will need to obey these three axioms. So firstly, let me actually define it. So which subsets of the set capital S is it going to contain? So tau restricted down to S is going to be the set that contains all subsets of the set capital S that are of this form: a set from the topology tau, so U, an open set from our larger topological space here, intersect the set capital S. Okay, where, as I say, U is going to be a set from our topology tau on the larger topological space X with tau here. Okay, so what you're going to do is you're going to go through every single open set in your topology tau here on the larger topological space here, and you're going to intersect every single one of those open sets with the set capital S, and what you'll end up with here, U intersect S, this will always be a subset of the set capital S, and you're going to put all of these subsets of the set capital S into this set, and that's what's going to become my topology on this set capital S, and it's called the topology from our larger topological space restricted down to the subset capital S. Now intuitively, in terms of the picture, what we're doing is if we've got some open set here that's in our topology tau, which is a subset of our larger set capital X, so here is our set U here, so from tau, so this is U from tau here. What we will do is quite simply intersect this with S and take this portion here, okay, this sub-portion, the portion that's actually inside of the set capital S, and that of course is going to be a subset of capital S, as I've written here, and we will stick that subset of capital S into this set, and that's what's going to form our topology on this set capital S. Okay, and this topology that you can put on this subset capital S is known as the inherited or induced topology from the larger topological space capital X with the topology tau. Okay, so we've now understood how this is a set of subsets of the set capital S. What we want to now do is make sure that it's going to obey the axioms of a topological space, or rather of a topology for the set capital S. So we need to make sure that it obeys all of these three axioms, okay, the axioms that this topology to be needs to obey in order to actually be a topology of S. So let's start off with axiom number 1. So axiom number 1 says that the empty set and the entire set must always be elements of the topology. Okay, so the empty set is a subset of our set capital S, and the entire set capital S is going to be a subset of our set capital S, and we want to make sure that these are going to be elements of this topology, the topology tau, restricted to S. Okay, so this is our first challenge. Now this is very, very easy to show. Okay, and why is it going to be so easy? Well, all I need to show is that there is some open set from my topology tau, which if I intersect it with S, will give me each of these two. Okay, so let's start off with the empty set. So which open set from my topology tau can I intersect with the set capital S to give me the empty set once again? Well, of course, the empty set is an open set in our larger topological space here. It's an element of tau, and if I intersect that with my subset capital S here, I will get the empty set back again, because of course there are no elements in the empty set. So when I intersect it with S, I'll get the empty set back again, and therefore it will be one of the things that I put into this set of subsets of the set capital S. So the empty set indeed is in this topology tau restricted down to the set capital S. Okay, so that's the first one ticked off. Now let's make sure that the entire set capital S is going to be in our topology tau restricted down to S. So what I need is some element of the topology on my larger topological space here, which will intersect with my set capital S to give the entire set capital S again. Well, how am I going to do this? Well, of course, one of the open sets in the topology tau will be the entire set capital X. Now, if I intersect that with S, what would I end up with? I'll end up with S again, because simply from this picture, the entire set capital X is this entire green box. The subset S is the orange circle. When I intersect those two together, I will just end up with the orange circle. So indeed, S will be put into this set of subsets of the set S, which is going to be our topology tau restricted to S. Okay, so first thing is verified that the empty set and the entire set S are going to be in this topology tau restricted to S, the inherited topology from the larger topological space. Now let's try and prove the second two axioms. Okay, so axiom number 2 then. So axiom number 2, what we want to do is take two subsets from my topology, so from this inherited topology here, I want to intersect the two together and prove that that will also be a subset that's in my inherited topology. So let's say I've got what I'll call U1 bar and U2 bar, and you'll understand why I'm putting the bars there in a moment. Okay, so let's say that these are in my inherited topology tau restricted down to S. So these are going to be nice subsets of S. So let me draw them on here. So maybe they look like this here. Okay, so just colouring them in here. Let's say this one is U1 here. Okay, so all of that there. So I might even colour it in like that. Okay, and U2 bar here will be the bit in turquoise here, so all of this here, and we can see that there's a nice intersection between those two there. Okay, what we want to now prove is that U1 bar intersect U2 bar. Okay, so the intersection between these two is going to be an element also of our inherited topology tau restricted down to S. So how are we going to do that? Well, we're going to again go back to our entire topology, our larger topological space, to actually work this out. And the way that we can do that is we can say, if U1 bar and U2 bar are elements of the inherited topology, then that must mean that there exists some U1 and U2, which are open sets in our larger topological space, such that when you intersect them with S, you get the U1 bar and U2 bar. Okay, so writing this out, here is U1, and we'll intersect that with S to get U1 bar. And the same for U2 bar, so we'll have some U2, which if we intersect it with S, will give U2 bar. Okay, so in our picture here, imagine replacing the larger topological space around this now. So this is our set capital X. You can imagine that these open sets, U1 bar and U2 bar, which are open sets in our restricted topology, that they came from intersecting these larger sets U1 and U2 with the set capital S. So U1 will be this set here, the green bit, plus the bit that's outside of S in the larger topological space capital X. Okay, so we could extend this here with green, and there is U1, and then when you intersect it with S, you end up with U1 bar. Similarly, for U2 bar here, there is this larger set U2, which is an open set in our larger topological space, such that when you intersect it with S, you end up with U2 bar. Okay, right. So now, if I want to consider what is U1 bar intersect U2 bar, it's just the same as U1 intersect S intersect U2 intersect S. So I can rewrite this as U1 intersect S intersect, so this is U1 bar here, so I've just stuck this in place of U1 bar here, and then we'll have U1 bar intersect S intersect U2 intersect S. Okay, so this is the same as U1 bar intersect U2 bar there. Okay, now what can we actually do with this? Because we can do something with this. Because what does this actually mean? Overall, this is going to be the set of things that are in U1 and S and U2 and S. That's what this overall means. It means everything that's in all of these sets. Now there is absolutely no point saying that it has to be in S twice. Okay, so we can instantly get rid of one of those intersect S's. In addition, it doesn't matter what order I actually write this in. I can write this as U1 intersect U2 and then intersect S. That's going to be exactly the same as this. All this says is ask what things are in both U1 and U2, and then of the things that are in both U1 and U2, then ask which of them are also in S. So overall it does just ask which elements are in U1, U2 and S. Okay, right, so that, I hope you understand, is the same as that. Okay, now why is this a wonderful thing? Because now I've got this written as U1 intersect U2, and remember U1 and U2 are both elements of my original topology tau in the larger topological space. So I'm going to intersect those two together and then intersect that with S. But we know something about if we take two elements of the larger topological space's topology and intersect them together, okay, that will give us another element of the topology tau. So this thing here, U1 intersect U2, that will be another element of the topology tau. So now that means this overall thing is some element of the topology tau intersect S, which is exactly the definition of what subsets of the set capital S that we are actually going to put in this inherited topology from our topology tau on the set capital S. Okay, so I hope you understand that we have now proven that U1 bar intersect U2 bar will always also be in this inherited topology, because we've shown that it's equivalent to some element of our larger topology, some open set in our larger topological space intersect the subset capital S here. Okay, right, so that's axiom number 2 checked, and then finally axiom number 3 checked. Okay, so what we want to show is that if we union together an arbitrary number of elements from our inherited topology, that we'll end up with another subset of our set capital S that is also in our inherited topology. Okay, so U alphas then are going to be elements of our inherited topology, and again actually I'll put a bar there. So they're going to be elements of the topology tau restricted down to S. Okay, and what we now want to show is that if we union them all together, okay, and remember again this alpha index, it could be finite, it could be countably infinite, it could be uncountably infinite, okay, it's very arbitrary. Okay, so we're going to union together all of these open sets that are in our inherited topology, and what I want to prove is that the subset that we'll end up with is also going to be in our inherited topology. Now it's certainly still going to be a subset of the set capital S, because if we union together loads of subsets of the set capital S, we will still end up with a subset of the set capital S. What we need to prove is that it's one of these special subsets of capital S that is actually well enough off to be in this inherited topology on the set capital S from our larger topological space. Okay, so how are we going to do this? Same tactic as before. We're going to say that if these U alpha bars are elements of our inherited topology, then that means that there was some open set in the topology on the larger topological space, which if you intersect it with S gives you that U alpha bar. So we'll call this U alpha. Okay, so for all alpha, it's possible to find a U alpha such that when you intersect U alpha with S, you will get U alpha bar. Okay, so remember, this is an open set in our larger topological spaces topology, and this is now an open set in our smaller set, capital S's inherited topology. Okay, right, so I can always do this. I can always find some open set in the larger topological space such that when I intersect that with my subset capital S, I get this open set in the inherited topology U alpha bar. Okay, so that means that when I'm performing this union here, I can replace all of these sets with this expression here. So what I'll end up with then is the union over all alpha of these sets U alpha intersect S. Okay, and what I need to now prove is that this is going to be in my inherited topology tau restricted to S. So to prove that, I need to prove that it's something in the topology tau of the larger topological space intersect the subset capital S. Okay, so how am I going to do that? Well, think what this says. This says union together all of these things, and what are you doing here? Before you actually union together these U alphas, you're firstly intersecting them with S. So each one of these U alphas, you're saying, firstly ask which elements in U alpha are also in S, and then union them all together. So you're firstly saying, okay, only take the elements that are also in S, and then you're unioning them all together. Can you appreciate that it's exactly the same as if I firstly unioned all of these sets together? Okay, so I could union together all of these sets U alpha and then intersect them with the set capital S, and this would give me the exact same answer, because here what I'm saying is union together all of these sets. So take all of the elements that are in all of these sets and then get rid of all the elements that are not also in S. Here, what I'm doing is, before I union together all of these sets, I'm firstly saying get rid of all the elements that aren't in S, and then union them all together. But those two different ways of doing it are going to still manage to chuck out all of the elements that aren't also in S. So they're actually going to end up doing the exact same thing. So in fact, this is equal to this, always. It doesn't matter that this index is potentially out of control. It will always work that this is equal to this. Okay, so that is exactly what we want then now, because these sets U alpha, they are from my topology capital, sorry, I keep saying capital tau, okay, on my larger topological space, capital X. Okay, so this is an element of tau. So I've managed to express this thing, this union over alpha of all of these open sets in my restricted topology, as some element of my topology on the larger topological space intersect S, which means that yes, this is an element of my restricted topology down to the set capital S. So indeed, when you do define this inherited topology on this subset capital S of a larger topological space, it does obey the properties of a topological space. So a subset capital S with this inherited topology on it is a topological space in its own right. Okay, and note something really important here. There was absolutely nothing special about this subset capital S. You could have taken whatever subset you liked and it would have formed a perfectly good topological subspace. Now if you contrast that to areas of maths like group theory and other branches of algebra, so field theory, ring theory, vector spaces, where it's only very, very, very special subsets that actually form subgroups or subfields or subrings or subvector spaces. Okay, here any subset you like can have an inherited topology put on it and will form a topological subspace. Okay, so this is much, much easier than in group theory, where it was only very special subsets that actually form subgroups. Okay, so we'll have a break here, and in the next video what we'll try and do is understand why this concept of a topological subspace is important.